Imagine looking up into the night sky and seeing not just the moon, but a pale shimmering band arcing from horizon to horizon, Earth's own rings. This isn't a scene from a distant alien world. It's a scientific possibility, a lost chapter of our own planet's history, backed by fresh simulations and intriguing clues buried in the geological record. Scientists now believe that Earth may have worn such a crown more than once in its deep past. These were not permanent fixtures, but brief, beautiful structures born from cosmic violence, sculpted by gravity, and ultimately erased by the relentless march of time. So, what exactly are planetary rings? The most famous example, Saturn's luminous disks, provides a starting point. They are a colossal collection of countless icy and rocky particles, ranging from microscopic dust grains to house-sized boulders, all orbiting in a remarkably flat plane. The key to their existence is a concept called the Roche limit, an invisible boundary around a planet where its gravitational pull is so strong that it overcomes the self-gravity of a passing body, like a moon or a comet. Inside this limit, the object is torn apart, its fragments shredded and smeared into a ring. Now, scale that idea down to Earth. Our rings would have been different, fainter, dustier, and composed of silicate rock rather than ice. They would have been temporary structures, constantly shaped by the delicate gravitational dance between our planet and the ever-present pull of the moon. How could such a ring have formed? The first and most dramatic hypothesis takes us back 4.5 billion years to the birth of our moon. In this chaotic era, the early Earth likely collided with a Mars-sized protoplanet, an object astronomers have named Theia. This cataclysmic event, known as the giant impact hypothesis, was unimaginably violent. It didn't just create a crater, it blasted a hot, glowing torus of vaporized rock into orbit around our world. Over thousands of years, much of this superheated debris coalesced under its own gravity to form the moon. But sophisticated computer models show that this process wasn't perfectly efficient. A significant amount of material would have been left behind, settling into a residual ring around the proto-Earth, a glowing, evolving structure, slowly raining its material back onto the planet's molten surface. For a time, our world and its new moon may have shared the sky with a brilliant, primordial ring. A second hypothesis suggests that Earth's rings weren't just a feature of its infancy. They could have reappeared much later, as transient phenomena following other giant impacts. An event on the scale of the Chicxulub impact, which wiped out the dinosaurs 66 million years ago, has the power to loft immense quantities of dust, molten rock, and superheated vapor high above the atmosphere. While most of this material would rain back down within hours or days, simulations show that some of it could achieve a stable orbit. The right impact angle and velocity could inject enough debris to form a short-lived ring. This dusty halo would cast delicate shadows on the surface below, a silent testament to the catastrophe, before eventually sifting back down over thousands of years as global showers of microscopic glassy spheres, known as microtectites and spherules. The third hypothesis doesn't require a direct impact at all. It relies on a gravitational near-miss, a process called tidal disruption. If a small body, a comet or an asteroid, ventures too close to our planet, passing inside Earth's Roche limit, the immense tidal forces would stretch and tear it apart. The object would be shredded into a stream of fragments. Unable to escape Earth's gravity, this debris would shear out and settle into a new ring plane, briefly circling our world. Such a ring would be unstable, a fleeting cosmic spectacle lasting perhaps only a few million years before atmospheric drag and the pressure of sunlight inevitably draw its particles down to a fiery end in the upper atmosphere. So, what's the evidence for these lost rings? It begins not with a telescope, but with a supercomputer. Scientists use high-fidelity N-body and hydrodynamical simulations to model the complex physics of a debris disk around our planet. These models are incredibly detailed, accounting for the gravitational pull of the Earth, the Moon, and the Sun. By running thousands of virtual experiments, researchers have identified clear stability windows, specific conditions where dusty or silicate rings around Earth could persist. Depending on the particle size, their altitude, and the complex gravitational resonances with the Moon, these rings could last anywhere from thousands to even millions of years. This isn't definitive proof, but it establishes a dynamic and plausible solution space. It tells us that, mathematically, Earth's rings are not just possible, they are feasible. The second line of evidence is written in the rock beneath our feet, though the language is cryptic and requires caution. Across the globe, geologists find distinct, thin horizons of spherules, tiny glass beads forged in the heat of asteroid impacts. We also find vast tektite-strewn fields, areas littered with larger glass fragments. While these are direct evidence of impacts, their global distribution could be explained by the slow, steady decay of a temporary ring. Furthermore, some ancient sedimentary rocks show finely layered patterns called rhythmites. It has been speculatively proposed that the regular shadowing from a planetary ring could influence climate and weather patterns, leaving behind just such a cyclical signature in the rock record. None of these signals are definitive proof on their own, but taken together, they begin to sketch a tantalizing picture of a world where dusty rings briefly dimmed our skies. The third and perhaps most compelling witness is the Moon itself. For billions of years, it has been a silent observer, collecting a record of the space environment around Earth. If our planet ever had a substantial ring system, the Moon would have been affected. Dynamical models show that some of the ring material would have been gravitationally perturbed and eventually swept up by the Moon. This could lead to subtle asymmetries in the composition of the lunar regolith, the layer of loose dust and rock on its surface, or unusual patterns in the distribution of small craters. The exciting possibility is that evidence of Earth's rings may already be here, locked away within the precious lunar samples brought back by the Apollo missions, waiting for the right questions to be asked and the right analytical techniques to be applied. If Earth did have rings, why don't we see them today? Because rings are not eternal. Several forces work tirelessly to dismantle them. The most significant for a dusty ring is the Poynting-Robertson effect. The simple pressure of sunlight saps orbital energy from each tiny particle, causing it to slowly spiral inward toward the planet. At the same time, for particles in lower orbits, the tenuous outermost layer of our atmosphere, the exosphere, adds a whisper of atmospheric drag, further hastening their decay. The solar wind and Earth's own magnetic field also stir and perturb the particles. Over thousands or millions of years, these combined forces cause the ring to thin, diffuse, and ultimately rain down into the atmosphere, burning up in a final graceful skyfall of meteor showers. If you could travel back in time to stand beneath such a ring, what would you see? It would be a spectacle unlike any other. From mid-latitudes like North America or Europe, it would appear as a thin, luminous band, a celestial causeway, tilted against the familiar constellations, stretching across the entire night. In the tropics, near the equator, the view would be even more dramatic. The ring would arch directly overhead, a brilliant ribbon of light, far brighter and more defined than the Milky Way. Because the rings would be made of dust, they would be most spectacular at dusk and dawn, catching the sun's rays long after it had set or before it had risen, a phenomenon known as forward scattering. This ethereal glow would shift with the seasons, a changing, silent crown above our ancient world. Artist's impression. So, what's next in the search for Earth's lost rings? The investigation is pushing forward on multiple fronts. Geologists are seeking to create better timelines of ancient impacts by studying deep-sea sediment cores and Antarctic ice, looking for telltale layers of dust and spherules. Others are conducting global micrometeorite counts to see if there were periods of unusually high influx from orbit. And crucially, scientists are proposing renewed analyses of the Apollo lunar samples with new technologies. Meanwhile, the next generation of N-body and hydrodynamical computer codes, now coupled to sophisticated radiation and atmospheric models, will allow us to test with unprecedented accuracy how rings form, how they cast shadows that might affect climate, and precisely how they die. The case for Earth's ancient rings is building, piece by piece. It remains suggestive, not yet final, a puzzle with many missing parts. But it transforms our view of our own planet, recasting it as a world with a more dynamic and dramatic past than we ever imagined. Stay curious. Support the work of the scientists piecing together this incredible story. With sharper data from the Earth and Moon, and bolder, more powerful models, we may soon be able to read the sky's old fingerprints and learn for certain how our world once wore a halo.